Hi, this is Alex Lamb. Today I have Gunter Klambauer from the University of Linz with me, and we're going to talk about his research, specifically this scaled exponential linear unit. Gunter is I believe, a postdoc. Is that right?
Yes.
At the University of Linz, where he works with Sepp Hochreiter, who is, of course, famous for creating LSTMs and being the first person to study the vanishing gradient problem. All right, so to kick things off, can you briefly talk about what the SELU, or scaled exponential linear unit, idea is?
Yes, so it's obviously an activation function, but actually the first thing I want to say is that we did not, or I do not consider this that we invented a new activation function, but rather a type of networks that are self-normalizing. So it's also focus on the paper is on this self-normalizing properties that I could show using this, if networks have this SELU activation functions plus initialization and other things. So it's not only the activation function. And in this paper, Self-Normalizing Networks, we could show that this type of networks have self-normalizing properties if you use SELU activations and the weights being a specific range. And the idea, so the main idea is to keep the activations close to zero min and unit variance through the forward pass. So this was, of course, the main idea of batch norm, layer norm, and weight norm, all these normalization techniques. The main idea was to keep the activations at zero min and unit variance. And my idea was, yes?
Why do you think normalization is a good thing in general?
So there is this in general. So obviously, practically, it's extremely good because you see the success of batch norm. But the main thing is, I think that that it has to do with the vanishing gradient that you talked before. Because if you keep the activation in a specific range in a similar range through layers, that would also mean that the gradient would be in a similar range between layers. And that's why the networks learn better. So when I saw all these publications, batch norm, layer norm, weight norm, I thought we could do this in a different way, namely to have this activation function that automatically takes care. You don't have to do something externally to the network. For example, a neuron wants to increase its activations, and then you learn that this neuron has a higher activation, and then with batch norm you subtract the mean activation again and stuff. So you do a lot of things from the network from the outside, but I want to just have a network that automatically has this property and then just train the network without interfering with it externally.
Right. Why would you say, though, that SELU is better than batch norm, at least in certain ways? Like, what would you say are the downsides to just normalizing the units to have a certain distribution?
Yeah, good question. So the first thing is, what's the definition of better? I mean, it can be
at least in some sense.
Yes. I'll come to that. So it could be with respect to computational performance, for example, and this means that of course it's better than batch norm because you don't have to compute the means and standard deviations of each neuron. You don't have to store it for each neuron, so it has fewer parameters and fewer computations. So with respect to computational performance, it's better, it's faster, less parameters. And with respect to convergence, I think we also showed that with respect to convergence, so if convergence is the criterion, so to say, we showed this in a figure that
So the paper has kind of an interesting argument that the variance in the gradient is worse when you're using batch normalization, and that's consistent with batch norm working well in ConvNets and not helping as much in fully connected networks. And that seems to be the main argument that's presented in the paper, if I understood it correctly.
Yes, yes. Okay, let me first finish the point before. So
Okay.
we had computational performance, then we had convergence, where I could say it's better, and then there is predictive performance. And with respect to predictive performance, it depends. I think we did large-scale experiments in the paper, but you cannot just expect if you change from ReLU to SELU that the predictive performance is better, because batch norm also regularizes. I mean, effects are known because you use in each. After each update, you of the batch norm parameter, you subtract a different mean and standard deviation. So this external thing that you do, this also regularizes. It's well known and sometimes also wanted, but this could have beneficial effects, of course, on the predictive performance. So this is another case, I would say. And what you're saying about variance of the gradient, of course, what we showed is that that by having to learn the mean and standard deviation of each neuron this of course introduces some variance to the gradient.
Yeah. I see. In terms of the variance of the gradient issue, with batch normalization, I wonder if you could address that by using really large batch sizes. I suppose, ironically, I'm actually aware of some work where they go in the opposite direction of, like, they use a really large batch, but then they compute batch norms separately over, like, subsets of the batch. And the idea is they want to get back the regularization effect.
Yeah.
But it seems like it would deal with the variance of the gradient issue. So
what's the concrete question? Yes, by making very large batches, of course the variance decreases. Of course, this would improve. You cannot make arbitrary large batches, of course, and also the batch size. So there was this paper on that some theoretical work. They showed that the SGD not only optimizes the original objective, but also the objective plus a regularization term that depends on the batch size. And so
I see. So it's possible that larger batch sizes reduce the variance, but they have some other negative effects.
No, I mean, not negative effect, but there are some other effects that come into play. Yes, one disadvantage, if you want, of batch norm is also that you cannot use it if you do online with single samples, for example. You cannot do for a single sample you don't have a variance. And with a SELU network, you can calculate the deltas and update, even if it's only a single sample.
Oh yeah, I see what you mean.
Yeah.
So can you explain the proof for why the SELU works at a high level? And by works, I mean the property that it achieves the normalization.
Yeah. So the proof, yes, the idea is that zero mean and unit variance is a stable fixed point.
I see. Yeah.
And to show this, you have to show that. So you have a mapping from one layer to the next. Maps the mean and the variance from next. So I give you a mean and the variance, and with this mapping, I can say, okay, in the next layer there is this mean and this variance. And now we have to show that this mapping has a fixed point at zero, mean, and unit variance, and this is a stable fixed point.
And I guess that it's the only stable fixed point.
Yeah, with Banach's fixed point theorem, you can also show that's the only one. Yeah, it's a unique. So there is this so-called contraction mapping theorem or Banach's fixed point theorem.
Yeah.
And if you can show that the assumptions hold, then it says that there is a unique fixed point that is attained if you apply the mapping continuously. So this means again and again. So this means what we have to show is that the norm of the Jacobian at the fixed point is if it's smaller than 1. If it's smaller than 1, then it's a stable fixed point. If it's larger than 1, then it's not stable. So we have to calculate the Jacobian of the mapping is critical, and it's a 2x2 mapping. It's a mapping from R2 and R2. So it's a 2x2 matrix, and the whole, and it's, I mean, there are a bit complicated expressions there, or larger mathematical expressions, but the work that we did is to show that the norm, or the largest singular value of this Jacobian, which gives the norm is more than 1.
When you're talking about the Jacobian, it's like the mu in the next layer with respect to mu and sigma previous, sigma on the next with respect
to exactly this Jacobian. So this one, and this Jacobian, it depends on 4 variables.
I see.
Which the old mean, so the mean and the variance in the layer before.
Yeah.
And then the mean of the weights and the second moment of the weight. And it's the influence of these 4 parameters on the largest singular value. Is a bit tough to show what's the influence exactly. And so the idea is it's basically very simple. So we just grid the space, and then we evaluate the function. We have a function, really an analytic expression for the largest singular value. We evaluate this on the grid points. This is what we need the computer for, and then we want to make a bound on. So the grid points are not sufficient to show if it's smaller than 1 on the grid points.
Because then it only holds on the grid points.
Yeah, it only holds, but we want to also show it between the grid points, and there we can use the to bound the values between the grid points. We can use the mean value theorem. There we need the derivative. And we have to bound the derivatives. And here is where all the mathematics stuff comes in. We have the derivatives of the largest singular value, and there we have to find bounds to be able to bound the derivative. And here, there's all these expressions with the error function and stuff, and there are some inequalities that we use to bound these expressions.
Yeah. So in the paper, are you just iterating over grid points?
No. So the iteration over grid points is not the main part of the appendix. The main part of the appendix is actually to bound the work is actually to bound the derivative.
Yeah.
And there is a section on how to evaluate the largest singular value, because I think it's not sufficient to just write the function and then in some programming language and then evaluate on the grid points. You also have, because there could be numerical problems with evaluating this expression. And so there's also a section where we show that the numeric evaluation is correct. So I think all the evaluations are correct up to 10 to the -8 or something, what we showed. So the expressions are typically not critical because you don't divide by values that could be close to 0, and the error function, it has some numerical guarantees when you evaluate it. So, but this is taken care of in a section on this computer evaluation.
Right. Is it simpler to show just that the 0, 1 point, just that's a fixed point?
Yes, that's very simple. That's
okay.
also in the main paper. So just the 0, 1 point, you just have to evaluate, and you see yeah.
Yeah.
But actually, yeah, what you're saying.
Wait, hold on.
Yeah.
It's more than just evaluating it, right? Because there's a bunch of different values the hidden states could take that have a mean of 0 and a variance of 1, right?
Exactly. That what I mean. We can very easily show that 0, 1 is a fixed point, but during learning,
Yeah.
the weights change, and we want Sepp and I also wanted to show that the self-normalizing property is still there, even if the weights are changed, and if a layer is away from zero mean and unit variance, if a layer has a bit of higher mean or a bit of a different variance, we still want to show that there is a fixed point. It's not at exactly 0, 1, but so this is we wanted to also have this self-normalizing property during learning, and this made of course the things more problematic mathematically.
I see. Yeah. So the SELU paper seems to have a number of automated proofs. Is that the case?
No, there are no automated proofs. With computer assisted, we only we evaluate the function on many points.
I see.
There are no automatic proof techniques that we used. Probably some of the pages in the appendix look a bit odd or full of formulas, and I think this comes from the fact that for some of the expressions we tried to find bounds, and we used Mathematica.
I see.
Bounds, and then we converted these formulas to LaTeX format. Then, but every formula is then checked and corrected by hand. But within Mathematica, it was just used to find bounds on some of the expressions, but there were no automated proofs.
Oh, I see. Okay. Yeah. Do you think that the theoretical approach of studying the fixed points could have applications elsewhere in machine learning? I mean, it's possible that it's already very widely used in places that I'm not aware of, but
yeah. So it's a very tough question. I mean, Banach's fixed point theorem or contraction mapping theorem, it's widely used for numeric algorithms to prove convergence. So it's relatively widely used and often used. It's a very basic theorem, basic thing. And I think what comes to my mind when you talk about fixed points is also, for example, in reinforcement learning, the Bellman operator. So Q learning, this Q star is a fixed point of the Bellman operator. So here it's also used. But otherwise,
I see.
I'm not sure where it could come up in future, but I'm pretty sure that it will.
Yeah. So another thing is with the SELU, one thing I noticed is that, like, for example, to use dropout with it, it requires some re-engineering of that, and like it requires like a specific initialization. So do you think going forward there might be ways of achieving self-normalization without kind of having to re-engineer the specific components of it? Do you see what I mean by that?
Yes and no. So I think what we basically solved is initialization, and with this dropout, I think there are still improvements that we can make even with dropout or other regularization techniques.
Right.
And I think what we would need, I think, is what is re-engineering is required, I think, also for architectures. So I think we have today we have this huge bias towards ReLU architectures. Because a lot of people use it from the start, of course, because they're really cool, and they develop their architectures, and there are different ways to develop architectures. Sometimes the people manually add layers or something, or some do it also with some hyperparameter search. But then after a huge process, huge tries, computational, hyperparameter search, whatever. But all this was done with Relo, and then we end up with architectures like ResNet and stuff with these large things. And then people sometimes expect now, if I change my Relo function activation to another activation function, it should work better. But through this development process, such that we finally come up with a cool architecture. I think from the beginning we had this huge bias towards Relo architecture. So with other activation functions such as SELU, or with self-normalizing networks, I think also new architectures are needed, are possible, and could provide also insights. And what you also asked, what re-engineering could be possible. So I think it's very well possible that there are other self-normalizing activations, or I'm sure that there are other self-normalizing. So to explore this space of self-normalizing activation functions would also be interesting.
Right. But I was also maybe wondering if there's some way that someone could get away with specifying like relatively arbitrary weights and kind of relatively arbitrary activations. And then the self-normalizing property could get pushed over to the like it would be like a penalty.
Yeah.
Optimized.
You mean introducing a penalty, or
that tries to make it closer to having the self-normalization property?
Yes.
That's just like a thought.
Yes. I think, that could be also a cool thing to like have a penalty term that penalizes it from being non-self-normalizing. Yes. Also, this direction could be possible. Yes.
Yeah, I mean, I guess one relatively simple thing in that is if you're training with the SELUs and it only has the self-normalizing property when the weights are at or kind of close to this specific initialization, if you had a way of forcing the weights to stay closer to that, maybe that would.
Yes.
Yeah.
Sure.
So how does, I guess my next question is, how does the SELU generalize to LSTMs and ResNets?
Okay, yeah, good question. So for ResNets, I think the question is how to both practically and theoretically handle the skip connections. So I think the characteristic thing in the ResNets, and so far, so we didn't cover this with the paper, and so far there is no theory on that, how to cover the skip connections. So you add something, but this is obviously not independent of the thing you already have. And so one of the options could be to adjust the SELU parameters after each skip connection to handle this additional variance that comes in. This could be a way to introduce here at this exactly where the skip connections are, to introduce a batch norm step. I don't know. So here some empirical investigations and also probably theoretical investigations have to be used. So I think the skip connections are critical and also here difficult with the SELUs. For LSTM, I think it's even harder because it's such a highly optimized, hard to improve thing, I would say. We have thought about it, of course, at our institute, how to use this. I mean, you cannot, at the gates, I mean, you need this, of course, the sigmoid functions or the, 10H, you cannot replace this with another because it's a gating function. So it's not straightforward how to use SELUs with LSTM. But I have to mention, I've stumbled across a paper that didn't get of attention, but I really like it. It's called, I think it's a flexible approach to automated RNN generation or something like that by someone from MIT. And what they did is they assembled new RNN architectures by kind of grid searching components. So they had these components like matrix multiplication, activation function, and they kind of randomly assembled an RNN, here a gate and stuff, and as far as I got it, that's what they do. And interestingly, in the selected RNN architectures that are quite strange and far from human intuition, that's what they also write. Often SELUs were selected as part of the model, and one of the tasks that they did was this language translation task with Bloy score and stuff. And I think the one with the best validation loss was a model with SELUs.
I see.
So,
So
I think, it could be beneficial in such things, because even in RNNs, but in the LSTM architecture, I don't see an easy way to use it.
Did it look like it? So I read the earlier, I guess, this neural architecture search paper. I don't think I've read the one you're referring to.
Yeah.
Did it seem to be using SELUs in a way that logically made sense to you, or was it something that was maybe not straightforward?
It's a bit I didn't look too closely into it. It seemed very I didn't get the architecture that was actually selected from looking at the notation that they had in the paper. So I would have to look closer into it, but at this,
I see.
Yeah, I didn't intuitively and very fast understand what kind of architecture this is and what the role of the SELUs was in this architecture.
I see.
Yeah.
From people's experience with using SELU, has anything in particular surprised you?
I might start off with something funny. So what I was surprised is that how frequently they were misused. So when I published this on Archive, in June, I think.
Yeah.
A lot of people were writing me, it doesn't work, and almost angry. And like 95% of all cases, they just used it with the wrong initializations. So what typically was the case is that they used he initialization, or I don't know, it's also sometimes called MSRA initialization, which is a default choice. And so it simply had the wrong initialization, and therefore it didn't work. The variance just blows up through the layers, and you cannot train the network. So this was a very frequent error, and I was really surprised that it happened, because in the implementation on GitHub that we pulled out, and also in the paper, we emphasized this a lot, that it's very important in which range the weights are.
Right.
Another thing there were a couple of things that surprised me. Another thing was that a lot of people expected like a kind of silver bullet. Someone also wrote this on Reddit. They thought that if we just change my activation function in my network from ReLU to SELU, the performance will be vastly better.
Yeah.
And I mean, actually, this happened quite a lot of times. So even at our institute, this happened. For example, in ERFnet, so that semantic segmentation, we just switched from ReLU to SELU, and it improved a lot, and we didn't use batch num. So actually, these cases exist, but you can expect it, because, as mentioned earlier, you develop this architecture with ReLU, so you're hugely biased with ReLU. You adapted all your regularization and stuff to the ReLU architecture, and if you just change the activation function, why should the predictive performance be automatically better? And then there was and a very positive thing also. Sorry, sorry for starting with the with the funny part. So I was really surprised that so many people started to use it. It was really great, even if there were some problems in the beginning. I mean, there were hundreds of GitHub clones. At the moment, there are 44 citing papers on Google Scholar. So in diverse areas, even non-machine learning researchers obviously read the paper or somehow noticed it. So in a lot of different areas it is used, and it's really great. I didn't expect that it would be impacting so many fields. And yes, one of the things was also that some people were a bit reluctant to use silos in CNNs.
Yeah.
And I thought that, so this is probably due because we didn't do in the paper we focused on feed-forward neural networks, fully connected networks. But so the reason behind that was actually that we expected people to say that silos would work in CNNs anyway, because the SELU is very similar to the exponential linear units, and exponential linear units paper was focused a lot on convolutional neural networks, and it is very successful for CNNs. So
Right.
we expected that people would say, yeah, what do you want? I mean, it's clear that it works because even the traditional ELO function without the self-normalizing property helps. So yeah.
I see.
Yeah.
What are other ideas in, I guess, activation function research that you find interesting? Although I suppose earlier you said that you don't necessarily consider it to just be activation function research.
Yeah. So activation function research, I think it would be, for me personally, I don't know if the community would be interested in that a lot, but the space of, as I said before, the space of self-normalizing activation functions, perhaps there are other activation functions out. Also, I think it's cool. I mean, you can come up with any other activation functions that you could think of, but I think they should have some nice theoretical properties that it could be not only self-normalizing property, but something like volume conserving properties. I would also be interested in the influence of the activation functions on the loss surface or the representable space. And yeah.
Yeah, that makes me think a little bit of there are these layers from let's see, what's it called? It's the nonlinear independent component estimation, or NICE.
Yeah.
And they're the layers that are sort of like the Feastal cipher, where they're exactly invertible, and they have kind of cool uses in generative modeling. And there's this recent RevNet paper where they have the neural nets with essentially no or very little memory requirement that uses those.
Yeah, so I'm not too familiar with these works, but I can imagine this would be an interesting thing as well. Yeah. And so, yeah, I mean, of course, I'm much, you're asking me about activation function research. I think a lot of things are going on. Papers are being published. I think people are researching this. And yeah, I'm of course a bit biased towards the SELU. I would also be interested if I could, if in a smooth, this SELU at the moment, it has this place where it's not non-differentiable, and perhaps there's a smooth version of the SELU that is differentiable everywhere. That could be cool. So yeah. I think activation function research is interesting and should be connected somehow with theoretical properties.
I see.
Not only empirical results.
I see.
You can say, for example, the cosine is my new activation function. And run a lot of empirical things, but and you see, okay, empirically it works well. But yeah, to have some theoretical properties is desirable, I would say.
Yeah, I think that definitely makes sense.
Yeah.
Have you or others tried using SELUs in Gans, to your knowledge?
Yes. So at our institute, many people use SELUs in Gans. They really so they work nicely in Gans as well. There are also I just checked this a couple of days ago. So there is an iClear paper.
Yeah.
That I actually like a lot. It's called, I've written this down, Thinking Like a Machine, Generating Visual Rationales Through Latent Space Optimization. So they trained again, both generator and discriminator without batch norm, which is quite cool. And we get that batch norm is without batch, so batch norm is helpful against this mode collapsing. So if a neuron has very small variance, batch norm would blow this up. So I think it has beneficial effects against mode collapsing, and similar things could be true for the SELUs. And there was another paper.
Wait, so if it's something that could be explained quickly, what do they do to prevent the variance from shrinking in the generator? Or how do they get it to...
This work, the Self Normalizing Network was sufficient.
Oh, they use SELU.
Yeah.
Okay, I see.
And in another paper on microwave-based hand gesture recognition, they even did some comparisons that I like a lot. So they compared ReLU networks with batch norm, with and without batch norm, against SELU networks with and without batch norm. And they explicitly state that the SELU networks have the same convergence quality as ReLU with batch norm. So for the SELU, the batch, if you do it with batch norm, it didn't increase, but with ReLU and the SELU is at the level of ReLU with batch norm. So that was, they even have this empirical results there. Yeah, like a lot. So yes, I think definitely in Gans they are helpful. They can be helpful.
Right, and it's interesting. At least in my experience, there are certain GAN architectures where it can be pretty confusing to use batch normalization.
Yeah.
Why?
Right. Why confusing? What do you mean by?
Oh yeah. So let's see. If you have, I suppose the idea is if you have two different types of batches and you apply batch normalization to them separately, you force all of these units to have the same mean and variance for a specific batch that you compute.
Yeah. Yeah.
Sometimes that property is undesirable. I mean, it's a little bit like using batch normalization in an RNN. Like you probably don't want every single time step to have the same mean and variance for the units.
Yeah. Yeah. Yes.
Right.
I think, yeah. Did you try the self-normalizing networks in this case where you have this confusing problems with the batch normalization?
Oh no, I haven't tried it in these cases.
Yeah, could be helpful.
Could be interesting.
Yeah.
Yeah. Have you looked into SELUs and reinforcement learning?
Actually, we have a group here working heavily on reinforcement learning.
Yeah.
And yeah, what I can, so at the moment, these are actually very experimental things because we're exploring, so research is going a bit in a different direction, but what comes to my mind with reinforcement learning in general is this the group from the NIPS Learning to Run challenge. You know the Learning to Run challenge? Or should I
I'm aware of it, yeah.
Okay, you're familiar with it. And so the second place was a group that used an ectocritic ensemble, and they used the SELUs, and you see that it improved a lot over ReLU. So they have these learning curves, SELU versus ReLU, and there it improved a lot. But in general, I would say in reinforcement learning, or the larger or the more complex the systems get, the more networks that you have to combine. Let's say you have a visual input, you have some textual input, and you have to combine it. So in general, where you have more networks having to interact or multimodal data sources, I think it's very beneficial if after a couple of layers, everything has the same distribution, and you can more easily combine it without having to externally learn how to combine the different representations or networks. And of course, the data sources, it can be sometimes you have continuous data with some distribution, sometimes you have very sparse distributions in input, but after using a self-normalizing networks, the neurons should have about the same distribution and you can more easily combine them. So I cannot foresee all the things that happen, but I think the more complex and the more networks are within a system, self-normalization property could be beneficial. That's all I'm saying.
I see. I mean, just in a practical sense, my understanding is there are kind of issues with using batch norm in reinforcement learning, just related to non-stationarity.
Can you elaborate? Can you explain more what you mean?
So like if you run with one batch and it tends to have like certain properties, I don't know, like it's all look like a character looking to the left, for example, the mean is going to be 0, and then immediately in your next batch things shift. And maybe it's like the character looking to the right.
Of course.
The mean gets shifted to 0 again. Maybe you want the unit's activations to be different for 2 different batches if the input X is sufficiently different.
Exactly. Yeah. Now I know what you mean. Of course, because if you change, if you change your way how you explore the space, if you have different state action sequences from a completely different space, you can also a lot of change the activation and stuff, and your old estimate for the mean and variance in batch norm is not good anymore. Yes, sure. So this can be problems, sure.
Yeah. What about the conditional batch norm technique, which some people, this isn't just for RL, it's a more general thing. But this conditional batch norm technique has kind of been used as a way of doing conditioning by learning different batch statistics depending on some conditioning information. And
I think what they do is they learn beta and gamma parameter from batch norm, right? That's
right. And I could quickly give a couple of examples of this. One is in doing like fast stylization, or trying to get a network that does this deep style thing. If you have separate batch norm parameters for each style image, that can make it work. I've also done some stuff, or I haven't done it, some of my colleagues have done stuff where I believe they do like image processing, and you have some text and you use the text to select the values for the batch parameters, or the batch normalization parameters, the beta and the gamma. So one thing I'm curious about is how would you see SELU fitting into this?
So first of all, I really like the idea to learn this beta and gamma from external. Of course, it can be applied, it can be extended to the SELUs, because if you know which mean and beta and gamma of batch norm are basically mean and variance, and you know what you have, you can adjust the SELU parameters. If you want a fixed point at 0.5 mean and variance 3, you can find the corresponding parameters of the SELU. So it's very straightforward to apply the SELUs in a similar fashion as conditional batch norm.
I have to think about that for a second.
So if you tell me where you want to have your fixed point, I can tell you the alpha and lambda value of the SELU.
Right, but it's kind of interesting because the idea here is that different examples would have different fixed points depending on the conditioning information.
Yeah.
But what you're saying is for every example, you would compute like a different alpha parameter. I forgot what the other parameter is called in SELU.
Lambda and alpha. Yeah, I mean, I don't know if I would do it if it performs well, but in principle, you can do it.
Right.
I'm not suggesting that you do it, that you try to estimate for each sample an alpha and the lambda, but in principle, for example, let's go to a different example.
Yeah.
As I said, with the skip connections in ResNet,
Yeah.
if you have your layer and with variance 1, and then you add something with variance 1, so this should have variance 2. So when you do the skip connections, then you adjust the SELU parameters to have a fixed point at variance 2 instead of a fixed point at variance 1. So this would be a case where you can apply it. In exactly this case, what you're talking about, where the conditional batch norm is used, it's hard to say whether it's, I cannot say whether it's very reasonable, but yeah, in principle, you can do something that is analogous.
Right. Yeah. So you could have something where multiple examples have distinct fixed points that they're going to, that are defined based on this condition information. Yeah. That's interesting.
I'm saying you can have this. I'm not saying, I'm not sure whether this is wise or it will work well, but you can do it.
That just seems like the most natural way to go into your thinking. Okay, that's pretty interesting. Yeah. Well, it's been a pretty interesting interview. Hopefully, for people who've listened, they've learned some interesting things about the SELU and the research from your lab.
Yeah. Thanks for inviting me for this interview. I'm happy to talk to you. Also, I'm looking forward to meeting you in person again.
Well, thank you. It was great to have you on. Have a great day.
You too. Goodbye, Alex.
Bye.